Riccardo BERTOSSA, who is PhD student of Stefano Baroni, I think in the last year of his PhD program, I think, and driving this hands-on session. So Riccardo has been also tutoring in the previous days. You might have meet him in some breakout room. Anyway, now I leave to him the stage and having the hands-on on ab initio molecular dynamics. Thanks, Riccardo.
Okay, thank you very much, Ivan. Actually, I will be the tutor of the tomorrow hands-on, so you will meet me tomorrow at the GPU hands-on. So now we are going to see what the Carparnello code can do in Quantum Espresso. So just a small introduction. So the Carparnello code is able to compute many different types of stuff. For example, the direct minimization of the total DFT energy that was the conjugate gradient that previously Sandro told you. Then is able to do Born-Oppenheimer molecular dynamics. That will be the first step that we are going to do later. Then, of course, the Carparnello molecular dynamics, where the electronics degrees of freedom becomes some sort of a classical coordinates, and they are integrated with the Verlet algorithm. Then it is possible, but we are not going to cover this in this tutorial, to do variable cell calculation. That is, you let the cell to become dynamical coordinates, so you can fix the pressure and simulate the system at a given pressure. Then the Nose-Hoover thermostat that we are going to use to equilibrate the system at a fixed temperature. Then an important difference that this code can do only gamma point calculation. That means you do not have to converge the k-point grid, and you have to check, of course, for the size effect that there can be present. So you can start with a small system, and then you can try the same simulation with a larger system and see if the quantities that you compute from the equilibrium simulation are the same or not. And then also other stuff that I don't say. So let's see what we are going to do today. So we will start with Born-Oppenheimer molecular dynamics. That means E equal m times A, and you calculate this with standard minimization of the DFT energy. Then we will use the ground state calculated within this Born-Oppenheimer simulation to start the Carparnello. We will see that to start the Carparnello, we need the equivalent of the velocities of the atoms, also for the wave function, because wave function are classical quantities in this Carparnello formalism. So we need the initial state, that is the ground state, and also the velocities of the wave function. And we will see how to compute them to initialize the simulation. Then we will see how to equilibrate the system at a given temperature. We need to set a temperature. If we start with the Newton equation, as you saw before, the temperature is not given. We have a fixed energy, and the temperature is what we have. So we have to equilibrate with the Nose-Hoover thermostat. After that, we will see that the system is equilibrated at the temperature, and we are able to run a longer microcanonical simulation. That means fixed the number of particles, volume, and energy. Where by energy I mean kinetic energy of the ionics degrees of freedom plus the potential energy, that in our case will be the potential energy calculated with density functional theory. At the end of the day, we will calculate the pair correlation function that was explained by Professor Scandalo before. and also another dynamical quantities that is the mean square displacement that is able to tell us, for example, if the system is liquid or solid, or if some atomic types are diffonding and other not, stuff like that. So for today, we are running a very small system. We will have a cubic cell with 8 water molecules. It is very small and very far from the thermodynamic limits, but it is enough for our tutorial. So just a small recap that for when I say trajectory, I mean the time series of position and everything that is calculated at every time step. We are using, of course, like every day, the Born-Oppenheimer approximation, and we are saying that the electrons are always in the ground state, and we are not treating nuclei as quantum particles. And that's it. So let's begin with Born-Oppenheimer. As was explained before, we have the Newton equations. So we compute this with the Hellman-Feynman theorem. And to do that, we have to select all the parameters that you selected in the previous day. That is the plane wave cutoff, which pseudo-potential you have to use. You don't have to select the K points because we use only gamma points. And then there will be additional parameters that are the time step in this case. So let's start by looking at the input file for our first step of our tutorial, that is the Born-Oppenheimer molecular dynamics. So you see this input file looks familiar. It is almost the same as the PW code. You set the title of the simulation, the type of calculation. You have many different types of the calculation. And now I'm reading the input description that you can find in the Quantum Espresso website. And also in your virtual machine, there is a shortcut in the Firefox browser. So as you see, there are many different calculations that are possible. Today we will cover only this one. The other are out of this tutorial. Then we have to tell the code that we are starting from scratch, because we will see that later we are using also the restart files that the code will write on the file system. So it is common with the Campanello to start from previous runs with the same code. So this after will be not from scratch, but will be another thing. Then this number means number directory write, and basically it tells the code the name of the directory where it is going to write the restart files that we will read later with the next step. Then you have to tell, of course, how many steps I want in my molecular dynamics simulation. Here, for example, we are doing 100 steps. Then this variable is important since usually the time step is very small. To compute the quantities that you want for your research, for example, let's say the pair correlation function, the G of R, you don't need to save every time step of the dynamics. And if you do that, you may end up with very large files that are useless because consecutive steps are very correlated. There is no so much information in 2 consecutive steps. So you can say, oh, I want to save 1 step every 10. So I have a lighter trajectory and enough information for compute all my quantities. Okay, this is telling the code that I want to write a restart file every 1000 steps. Here we don't reach 1000 steps, but suppose you're running a much longer simulation. Let's say that runs for a day on a supercomputer. And suppose at a certain point of the day, the supercomputer crashes as it can happen. It happens to me a lot of time. And what you do, you don't want to lose the computation of all the day, so you tell the code to write the restart file every 1000 steps. That can be, let's say, half an hour, 1 hour, whatever. So later you can restart from the last restart file written. Then this is not necessary. This tells to write the forces in the trajectory files. Later we are going to see the trajectory files. Write forces. Then the time step. Okay, the time step is in units of atomic units, and here there is a very delicate point. This is taken from the documentation. This is very important that the atomic units of the Carparnello codes are different from the PW codes. So there is a factor 2. So here in Carparnello, the time atomic unit is this value here. In PW is twice that, so 4.8, etc. Okay, this is very important. So here we set this to 5. It is a really small value if you think about it, and it is useful at the beginning of the simulation to set a small value, especially if you choose an initial state for initial atomic position that you guessed and you're not sure if they're good enough or not. So you could, for example, end up with 2 molecules that are too near each other, and if you choose a time step that is too big, maybe this atom displays too much, and you will not sample with enough accuracy the trajectory. So at the beginning, it's useful to use a very small time step for the Born-Oppenheimer standard time step. Okay, prefix is just the initial part of the name of the trajectory files. This is standard. Then we are using a cubic system with a size of 13 Bohr radius. We will have 24 atoms of 2 times hydrogens and oxygens. Okay, the cutoff you have to converge as in the previous exercises. Here I choose a pretty low cutoff just to run faster the exercise, but you have to check that the forces and the energy are converged within this cutoff. So this is something that you have to check. This is in replay. Then, okay, now we tell what to do with the electronic degrees of freedom. We tell the code that we want to do at every time step of the dynamics a conjugate gradient minimization of the electronic degrees of freedom. Here the codes for the first step will start from scratch. So we set, I think, a random wave function or some educated guess. Then at the next consecutive time steps, it will use the previous solution of for the ground state to start with, and then it will minimize this initial guess that is a lot better than a random electronic wave function, for example. So you can see, if you look at the output, that the first step take very little time, then very long time for the first step, because you start from scratch. Then for all the other steps, it will be much faster. Then here we say, hey, I want the Newton equation, and I want to integrate them with the Verlet algorithm for the ionic degrees of freedom. That means the Ri. All these quantities. Then, how do I select the initial velocities of the atoms? Here I tell the code to sample from the Maxwell-Boltzmann distribution, that is something like a Gaussian, where you have the square of the velocity of the atom times Q kBT. Okay, so you use this distribution. This is not normalized. Of course, you have the normalization factor in front. You sample the velocities of the ions from this distribution with a temperature that is 600 kelvins. Okay. Then you have the rest of the input. Okay, this forget about this. It's not necessary. I don't want to move the cell. The cell is fixed during all the simulation. Then the pseudo potentials and all the atomic position as in the PW code. Then you can see there is an additional okay, let's go to the director maybe. Today is day 8. This is the first one, the first input file. At the end of the file, here you have all the atomic positions. Sorry. Okay, all the atomic positions. Then at the end of the files, you can have a special card that is specific to the Campanello code that is able to tell the code to change some parameters of the simulation during the run. This can be useful, especially with the first step of the simulation, because you don't have to write a lot of input files. So for example, here, after 10 steps, I use a bigger time step. Why? Because suppose that I am in this situation where two atoms are too near each other. After 10 steps, I suppose, but I'm guessing it is not a rule or anything. I'm supposing that this situation is fixed, let's say, so I can use a bigger time step. With the Born-Oppenheimer molecular dynamics, maybe you can use also time step bigger than that. Okay, this is typical with Born-Oppenheimer. Then at the end, I set again a small time step because this is the time step that I'm going to use later for the Campanello simulation. I will explain later why we are using a smaller time step with Campanello simulation. If you don't do this and you change the time step between different restart files, that means you start, you do the first input with, let's say, the time step equal to 20 atomic units. Then you stop the simulation, you write the restart file. If you want to restart the simulation, but with a time step, for example, of 5 atomic units in place of 20, you have to tell the code with an input that is this one. You have to tell the code that you changed the time step. Why? Because in the restart files, there is no the velocity of the velocities of the electrons and of the ions is not saved. You have only the position at 2 consecutive time steps. So if the code does not know what was the old time step, it cannot rescale the position at the time step before the last one to have, let's say, correct velocities in the algorithm. So you have to tell this if you change the time step between different runs of the code. Okay. So I think I said all. We can try to run this. Okay, to run this is very simple. Okay, this is here we are the input file. So just check that you are connected to your cluster. With maybe you have to run the VPN stuff. I've already run it. I just have to type remote MPI run. Sorry. MPI run. Okay, this one. Just a trick. If you press, you know, okay, it's going. If you press Ctrl R, you can look at the history of your bash. For example, here I pressed Ctrl R plus R. Then you start typing and you can search in your history. This is very useful when you want to keep a previous command. So this should be very fast. And let's see if it works. Remote school. Okay, it is running. So now we are running Born-Oppenheimer molecular dynamics. Okay, I see the how do you select the initial position of the water molecules? Okay, this is a very good question. Actually, I I guessed it. In this particular cases, I selected, I put one molecule oriented randomly in the space, and I used some symmetry group operations to move them, to move it around the simulation cell. I do stuff like that. So it is some sort of art to select the initial position. Usually I suggest to pick the crystal one if the crystal is simple, or to maybe also start with classical molecular dynamics, pick some equilibrated position of your system and use this as a starting initial position. There are also a lot of programs and codes that help you to build the initial state for the positions. So let's see if it finished. Oh, yes. So now I copy back. Okay, I copy back from the cluster. I think from APC. There are a lot of files. You see in the list. You see, okay, the trajectory files. Those are all the files that the code generates at every time step. Then you have the restart files that are the files that we're going to read later to start the next step. So let's have a look to this. Just have a look for the moment. Later we will plot it. So you see there is here. Let's start with the cell file. You see, this is the prefix H2O. The cell file is very simple. Is the cell vectors. Since the cell is constant, they are always the same. You see, this number is the number of steps. This is the time in picoseconds, not atomic unit. These are picoseconds, and then you have all the cell vectors. You see the cell is cubic. This was simple. We can see the positions that are the most interesting one. The position file. Okay. You see the first line, let's say the header for each time step is the same as the other file, number of steps, and time in picoseconds. This is different, time in picoseconds. Maybe I will write it. Time in picoseconds in H2O dot whatever files. Then you have all the atomic position in units of Bohr radius. Okay, so the positions are in Bohr radius. And you see, no, maybe you now we don't see because we are not looking at it graphically, but the order of the position is the same as the input file. So if you put the atoms in some order in the input file, here you find the same order. Note that I've written this question, this sign here, because this changed in version 6.6. Before they were sorted by type and then by input file. So this changed. In the last version, it is the most intuitive way of writing them. Okay, the velocities is the same, but with velocities. Here, time is in the same atomic units as before. So between velocities in Carparinello and PW code, there is a factor 2. Then there is the EVP file that has some thermodynamical information on all the quantities that, for example, number of steps, time, picosecond. This we will see later what it is. It is the kinetic energy of the electrons, but now since we are not running Carparinello, it is 0. Temperature of the cell, if you are moving the cell, for example, then the temperature of the ions, that is something that we are really interested in. Then you find the a thought that is the potential energy of the system, the DFT energy. Okay, entropy. A cons, it is. Did I write it later? Okay, yes. A cons is the potential energy plus the kinetic energy of the nuclei. That is the energy that is conserved in a classical molecular dynamics simulation. Then a cont, it is the constant of motion of the Carparinello Lagrangian that now is not conserved because we are not running Carparinello. Okay, volume is constant. Pressure, we are not computing the pressure, so it is 0. You have to tell the code to compute the pressure if you want it. So maybe we can see also what happened. I prepared a little script to run some conversion tools that are not specific to quantum espresso and just are useful to see the results of the simulation. And then I can open the trajectory that the script generated with Ovito, that is a program just to visualize the atoms. So what happens? Okay, this is my system. You have a different view of the same system, top, bottom, right, left, everything. You see our 8 water molecules, and there is not much trajectory in here. We have 9 frames, so you see the atoms move really a little. So that's it. We are ready to go to the next step. Okay, this is a slide just to remember you what does the code write in the restart files. So remember the restart files is specified by this NDW, number directory write, that is the number appended here. So this is 50 NDW. And inside you find all the data that the code needs to restart the simulations. Okay, now we move to the next point that is a little bit delicate. So, did I write the campaign? Okay, maybe let's move to this before. To do molecular dynamics, it is useful to express the system in terms of Lagrangian. That is an expression that together with the Euler-Lagrange equations can define the equation of motion for the system. So in particular, this is the Lagrangian of the Carparinello method. Okay, my important points are, these are the equations that we need to integrate with the Verlet algorithm. So you see that there are some parameters, but before the parameters, let's focus on the equation itself. It is a second order differential equations. So to integrate a second order differential equations, you need the initial conditions. That means you have to provide the 0th derivative of your function at the initial time step at t equals 0. That means the position of the atoms, Ri, and the initial wave function, that is the ground state. Then you have to give also the first derivative of these two quantities, so the velocities and the derivative of the wave function. Now, the problem is, what is that? Okay, we could, in principle, set this to 0. Don't worry about the parameters. I will explain them later. So this, how to guess this? One can think, okay, I put it to 0. It is okay also to put it to 0 at the beginning, but it is not really physical. So what we want to do is to find a way to estimate the wave function velocities for the initial condition of the second order differential equation. So, as I said, the nuclei for the nuclei, this is simple, but for the electrons, what to do? It is not possible to do this. That means this is not possible because this and this can have different gauges. Because the minimization of the ground state is independent. Nothing, nobody told the conjugate gradient algorithm to choose the same gauge for the two minimization. They are independent completely. So if you do this difference, let's say, for example, that this here there is a different phase. You are subtracting something that is not correlated, and you get only random numbers. So what we do is to do a trick, to use to fix the gauge practically, and we use the parallel transport gauge. That means we want to compute this. Okay, let's write something trivial. We write the projector over the occupied manifold. And we say, okay, the wave function is equal to the projector to the occupied manifold times the wave function. I've written nothing here. Now let's do the derivative. I do the derivative of the projector, then over the wave function, and the parallel transport gauge that I will not explain here in the details, but it is equivalent to say, okay, I put this term, I define this term as equal to 0. In this way, we are able to compute this because this object is well defined also with if I use the finite difference method to compute the derivative. That means it does not depend on the gauge that the minimizator, the conjugate gradient choose to compute the ground state. So we do that. We compute this, and we differentiate it numerically, and we use it to compute a new state at time t using the previous step at times t minus dt and this object. Okay, in this way, you see that if a particular gauge is selected for this wave function, it is selected also for this is the same one, and this will have the same gauge. Same gauge as t minus dt. So we are okay. We are ready to start the Verlet algorithm. A little note that right now this is implemented only for non-conserving pseudopotentials. So if you don't use non-conserving, you will have to start with the velocity of the wave function equal to 0. Okay, now since we are moving to Carparinello, I will start to explain you the parameters of the Hamiltonian and the Lagrangian. So I can say this. So you see, there is this mu that is a mass for the electrons. You can imagine the electrons I like to imagine the electrons are some sort of classical fluid. Like you have the potential, you have a bowl, let's say, you have some water inside it, and this water has a mass that is mu. Okay. Then there are other stuff that maybe it's not very important, but you have to know that it exists, that are orthonormatic constraints that are needed because you want the wave function to be orthogonal to each other. So there is a standard method in Lagrangian mechanics that is to put some Lagrangian multipliers that are here only to ensure that the wave function are orthonormal each other. So these are quantities that are computed by an iterative algorithm and produces some sort of additional forces on the wave function that make sure that the wave function are orthonormal each other. Okay, then, okay, explaining this is the electronic fictitious kinetic energy that is called Ekin C in the output files. That is the equivalent of the kinetic energy of the nuclei, but for the electronic degrees of freedom. But here is by far more complicated because you see, you don't have here you have, for example, we have in our case, we have 24 atoms. But here we have a lot more degrees of freedom. That is the number of plane waves that is called NPW, for example, times the number of bands. So you have a lot of degrees of freedom inside here. And the kinetic energy of all these degrees of freedom is called the electron fictitious kinetic energy. In the code is written Ekin-C in the output files also. So that's it. Then the mass parameter. How to choose the mass parameter? Okay. As Professor Scandalo told you before, what we want to do is to have this potential. We have, let's suppose for simplicity that the electrons are like a fluid, like water inside a bowl. The potential moves, and we want that the water moves with the bowl and does not go outside. So suppose, for example, that you use a very large mass for this electron, for this water inside the bowl. It will be very difficult to move the balls, and if this is an ion, you will have that the mass of the ions is like the mass of the ion plus an additional mass that depends on the mass of the electrons that are attached to the ions. I repeat again, electrons are like some classical fluid that is attached to the ions by the DFT potential. So if you choose a mu, an electron fictitious mass that is too large, you have these issues, but this is not all. You will have another issue that is the issue of the coupling between the electronic degrees of freedom and the ionic degrees of freedom. Maybe I can add another. So what is the issue? It is that we have two systems, different systems. We have the ionic system and the electronic system. We want that the electronic system stays always cold. That means the electrons are near the ground state and keeps oscillating near the ground state. But what happens if the two systems exchange energy? Since the electrons are very cold, and the ions are hot because they have a temperature like a few hundred degrees or kelvins or more. If there is an overlap between the frequency of the ionic system and the frequencies of the electronic system that are very fast because the electrons are light, if you choose a low enough fictitious mass, if there is an overlap, let's suppose that those are the frequency. This is the ionic frequency, and this is the electronic system frequencies. If there is an overlap, the energy will start to go from the ionic system to the electronic system. So what happens is something like that. The energy of the electronic system goes up, and eventually the electrons will go out of the ground state, and you will end up with very expensive random numbers. So what you want is that the highest frequency of the ionic system is smaller by a big enough amount of the smaller frequency of the electronic system. And it turns out that, oh, I duplicated the slide, okay, that the smaller system of the electronic system is proportional, like I call it mean. The smaller frequency of the electronic system is something that goes like the gap, the electronic gap of the system over the fictitious parameter over the square root. So you see, if you put here a too large number, eventually this small frequency will overlap with the frequencies of the ionic system. Energy will exchange, and the electrons will go away from their ground state. So as a rule of thumb, I start with an Emass, that is the name for the mu parameters in the input file, of about 15 units of atomic units, Hartree atomic units. That is a reasonable enough value that usually allows to have a good allows the electron to follow the minimum very well. Then there is another thing on the other side, that since you are integrating the electronic degrees of freedom with the Verlet algorithm, and you want a long enough simulation because you want to simulate, for example, 1 picosecond, let's say. If you choose the lower the mass that you choose, the faster will be the oscillation of the electronic degrees of freedom, because they are lighter. If you have a lighter object, it will run faster. In the Verlet algorithm, there is a part, as you saw before, that is something like that. You have a mass, then you have delta t square. So if you divide this by 2, let's say, to have the same magnitude of the displacement, we have to divide also this by the square root of this. So the lower the electronic mass, the lower the time step. And since the electronic mass is the lighter element in the system, you have to choose a smaller time step for the whole simulation. So you have to balance between a small time step and an accurate enough simulation. This usually is a good guess to start with. So let's go through the input file. Okay, calculation restart. Maybe let's see it. Sorry for being long, but there are a lot of concepts here that I find very interesting, by the way. So CP molecular dynamics. So you see, we have to change a few things. We want a restart. That means we want to read the ground state and the electronic velocities from the restart files that we calculated before with the previous run, and with the velocities calculated with the projector trick, let's say, we have to tell the code number directory read. That is the number that identifies the folder where the code is going to read the restart files. Then you have to tell number directory write, and I increased this by 1 to not overwrite the previous directory. So if I want, I can restart again from the previous calculation. Then I want more steps, and since Carpanello is usually cheaper for steps, for a single step, I can put here a much bigger number. Then this is very important. This switch on the Carpanello equation of motions. So if you tell the code electrodynamics equal to Verlet, that is here in the electrons name list, we are using the equation of motions of Carpanello. Then the last very important thing is to set an Emass to a reasonable value. You can start from this and then see if it is possible to increase it. Then we will see how to check that Emass is good enough, or decrease it if the simulation does not goes well. As I said before, if you choose a too large Emass, it can happen that this becomes too low, and the electronic system and the ionic system exchange energy. Electrons heats up, and everything goes bananas, as the code will tell you. Ion velocity is equal to default, tells the code to read the ion velocities from the restart file. Remember to not forget here random, otherwise velocities will be overwritten with the new one velocities, and also the autopilot card is not necessary anymore. Okay, everything is the same. So now we can submit also this. I use the reverse search trick that I like very much. So remote NPI run close. And if you press Ctrl R and more time, you see the command. So this is step 2. Carpanello molecular dynamics.in. So I run it. I hope that I'm not saying too much stuff. Okay, somebody asked what is a K nuclear. Maybe I did not explain it better enough. So this is okay. The DFT is this one. DFT of the previous slide. Okay, this is K nuclei. I called this part. This part is the kinetic energy of the nuclei. And this is the kinetic energy of the electrons. Okay, now we are going to see in more details the output, because we will have more. So let's see if something happened. Now we will see in details all the output and why some parts, some energy changes, some other energy does not change. And so, okay, it worked. Sync from APC. You see there is a new folder of the new restart directory, and the trajectory is updated. An important thing, if you keep the same prefix for the trajectory, every time you run the code is going to append at the end of the file the new quantity. So it is not going to overwrite the file, but it is going to append new atomic position, new atomic velocities, new cell vectors, new thermodynamical quantities at the end of the file. So don't worry. And the timestamp, the number of times is always increased between each restart file. So when you run the new input, the first step will be the number, with the same number of the last step of the previous run. So I already showed you how the output appears in the terminal, but now let's use a new plot. I prepared a small script that it's nothing special. You can see it. It plots some columns of the output files. So I will run it. Plot thermo. I don't know if you know, but if you press tab in the terminal will try to autocomplete what you're writing, so you can type faster. Okay, I hope that is clear enough, these plots. So what we are seeing here? We are seeing the output of, let's put the grid. The thermodynamical output of the code. So you see here there are the few steps that we ran before with the conjugate gradient algorithm. Then here at this point we switched off conjugate gradient. We did the restart file. Illegal extraction, very nice. We did the restart files, and from this point on, we are now running the Carparinello algorithm. So here I'm plotting. This is the constant of motion, this line in between. Maybe I can zoom. Okay, you see this line here. This line here is the constant of motion of the Lagrangian. Each Lagrangian has many constants of motion, and if the integration time step is small enough, this constant of motion will be constant within numerical accuracy. That means that the parameters of your simulation are good with respect to the Verlet integration. So it does not mean that your simulation is good. This means that the time step, the delta t, is small enough. Then I printed the electronic kinetic energy, that is this quantity here, and I shift it from this point. So the electronic kinetic energy is only from here to here. It's only this one, and you see that is approximately a constant. So if the simulation is good, this electronic kinetic energy will be more or less almost the same during the simulation if the temperature does not change. That means that there is no exchange of energy between the ionic system and the electronic system. That in turns means that probably the forces that you are calculating are good enough. So you have to check when you run the Carparinello equation of motion that this kinetic energy of the electrons is always the same. If it is always the same, means that there is no energy transfer between the nuclei and the electronic degrees of freedom. So you can trust the forces that the code is computing for you. Then, okay, the constant of motion is nothing physical. It is not like the energy of a classical simulation because you have this term inside it. So the constant of motion, maybe I wrote it before. Yes, a cont. This is called a cont in the output file. It is the potential energy. This is potential energy. Plus the kinetic energy of the ions, that is something physical, plus this part. This part is not physical, there is no physics inside this number. Because it is only an energy that arises from the way that you are using to minimize, let's say minimize, but it's not a true minimization. You saw before. It is a kinetic energy that arises from the way that you're using to compute the forces at the end of the day. So it is not related to a physical quantities. Also because if you change a mu, if you change the fictitious mass of the electron, this number here, the kinetic energy changes, so it is not something physical. So this constant of motion is something useful to know if the simulation is good, but it's not something physical. The physical energy is the sum of the nuclei kinetic energy plus the DFT potential energy, the DFT energy. That is this line here under the concept of motion. And by the way, you see that it is evident from this plot that the concept of motion is this plus the electron kinetic energy. You see that the plot are mirrored around the constant of motion. So if your simulation is good, or is if your simulation is good, the physical energy, the physical total energy of the system will be more or less a constant. Okay, then let's see if I have to say something more. Okay, the potential energy, also in this case, when the system is equilibrated, the potential energy will oscillate around a constant value. That is okay. In this case, the system is the simulation is very short, so it is difficult to say if later this energy will stay more or less constant, or it will go up or down or whatever. So, but since now it seems everything seems okay. So then, okay, here I wrote something about the forces. You can. Okay, the forces, as I told you before, and also as Scandro told you before, forces are not exactly the one that are given by the PW code, for example, because the ground state keeps oscillating in the minimum of the potential, and it is not always exactly the same, but on average, the forces are about the same of the one that the code pw.pix calculates. But there is another fact that maybe you can imagine, that if let me put another time. Okay, if let's say that is the potential, here you have the electronic degrees of freedom that has a mass. So you have a mass that is added to the ionic mass. How is this reflected in the forces? It is reflected in the fact that the forces calculated by the CP are a fraction of the forces calculated with the true Born-Oppenheimer method. And this is something that is usually like 99, something like that. So it is nothing that you have to worry about, but be aware that if you put this too large, this number can go to something like 0.8. So you have, if you are computing statical properties of the system, those does not depend on the mass of the ions plus the electrons, let's say. But if you're computing dynamical properties like diffusion coefficient, you have to be careful, because if you choose a mu such that the forces calculated by Parinello are off by a factor of this, you are computing wrong diffusion coefficients. So be aware of this fact. So here I was suggesting to compare the forces a part of the factor 2 with an electronic mass of 50 atomic units. You should not see nothing strange. So you should see that the forces are more or less the PW1. Okay, so this is done. Now let's move to the next step. How we can choose the E-mass of the electrons. I told you before, you can start with the E-mass of 50 or something like that as an educated guess. Then you can check, first of all, if there is no transfer between the ionic degrees of freedom and the electronic degrees of freedom. That means that in the plot of the kinetic energy of the electrons, the kinetic energy of the electrons remains more or less constant. Then, as a last step, you can check the ratio between the forces calculated with the Parinello method and the forces calculated with the Born-Oppenheimer method. If the mass is low enough, the forces would be similar within oscillation typical of the Parinello method, but that are not harmful to the simulation. Okay, then let's start with this thermostat. So, as Sandro told you before, if you start with an initial condition chosen randomly, let's say, you will never get the temperature that you want. So let's switch on the thermostat. Why there are these two? Okay. Thermostat. Let's. Well, what did I do? Switch text. Very nice. Go away. Okay. Vim water 8 3 non sei over. So increase by 1 number directory read and number directory write. As always, we don't want to have a write restart files, because we may want later to restart from a previous step of the simulation. So we increase this. This has to point, of course, to a valid restart directory. Then I want more steps. 5,000 looks to me enough. Here there is no precise recipe. It depends really on the system, the time needed to equilibrate at a given temperature. You will have always to look at the output files and see if the system is equilibrated or not. So to switch on the Nose-Hoover thermostat, we have to put in the name list ions this and the temperature in Kelvin. Oh, very nice error, by the way, on the Slack chat. So where is this? Okay. You see, ion dynamic Verlet, ion velocity is default. That means you copy the velocity from the previous restart, the temperature of the thermostat, the ion temperature nose. Then there are 2 additional parameters that are very technical. I will not explain them. If interested, you have to study the way the Nuse-Hoover thermostat works. But just you have to know that there are additional parameters that are explained here, for example. You see ions. You have FNOSEP that is explained here. It is just a parameter that you can tune to have a better equilibration at your temperature. And also this is the number of chains in the Nuse-Hoover thermostat. It is a very technical thing. Just you know that they exist. So if it is difficult to equilibrate your system at a given temperature, you can try to change this parameter and see what happens. This usually you can choose so it overlaps more or less with some peaks in the vibrational spectrum of your ionic system. Okay, so let's submit this to the cluster. Where is my information? So remote MPI run, and it is step number 3. Nuse-Hoover.in. It will take a little bit.
Ricky, sorry,
Yes.
now that are you're waiting, there are questions on the YouTube. If I
Yes.
particularly one ask if I can use any time of any kind of pseudo potential for the Capparinello.
As far as I know, yes, but be aware that, for example, the wave function velocities feature that we used at the end of the Born-Oppenheimer step that we did first before, it is implemented only for non-conserving pseudo. So there are some features of the code, usually the more advanced they are, the less the number of pseudo potential types that are implemented. So, for example, for non-conserving, you have everything implemented, and but yes, there is no. You can use whatever pseudo potential you think is good enough for your system. For ultra soft pseudo potential, there are additional parameters that maybe I'll explain here in the input file. That is this number here. It uses a different algorithm with respect to the PW code, and you have to specify this number for the ultra soft that are some sort of grid that is around each atom to contain the additional charge, if I'm not wrong. Okay, so be aware if you use ultra soft, there is this additional input that you have to provide, and then yes, you can use whatever you want.
Then there is another question if you can use the optimized gamma trick.
Everything is gamma trick.
Exactly.
Because we have only gamma point, we don't have k points. So you have to check for convergence with respect to the system size in place of the convergence with k points, and the codes use only gamma tricks. Then okay, then NOSEP parameters, you can leave the default basically. The recommendation is if your system does not equilibrate fast enough, you can try to plot the vibrational density of your ionic system and try to choose a value that overlaps with it. For example, in my case, I put 10. Not wrong. Yes, I put 10. Okay, this is a frequency in terahertz that has to overlap in a good way with your system to enable a faster exchange of energy between the thermostat degrees of freedom and the ionic degrees of freedom. But it's really technical, this one. It's better to do some trial and error and see what happens after reading a little bit of theory, of course, so you know more or less what you're doing. Okay, I think that maybe the code finished. They are all very fast run. Remote where? Yes. Sync from APC. Oh, the new trajectory. So no say over. Okay, now we do the same step as before to see what happened. So our friend GNU plot. Let's plot the same stuff. Oh, interesting. So you see the data is always appended at the end of the file. Here at the beginning, you have the plot that we had before. So this is exactly the plot that we had before. But then we switched on the Nosé-over thermostat. From this plot, what you can see, this is the physical total energy, that is the kinetic energy of the ions plus the potential energy for the ions, that is in this case is the density functional theory total energy. You see that it starts to oscillate. It is no more an approximate constant of motion, because I remember you that the exact constant of motion is the one that includes also the electronics degrees of freedom, plus, of course, the thermostat degrees of freedom, that are the additional variables that you introduce in the equation of motion to fix the temperature. You see that it changes because you switched on the thermostat, and more or less after a certain time you see that it starts to oscillate around some values. So it looks like the system wants to equilibrate around this physical total energy. Then you can see that the electronic kinetic energy went a little bit down. Why did it went down? Because the temperature of the system is lower. By the way, later I have to show to you also the temperature, of course. And you see also that the constant of motion of the Lagrangian is a constant of motion. So we are happy that our time step is small enough. So it looks like everything is going well. This is the potential energy. It is equilibrating around another different values, of course, because we switched on the thermostat. And okay, let's see the temperature. The temperature is column 5, I don't remember. This is later. 5, yes. Okay. You remember that at the beginning we chose a temperature of 600 Kelvin for the initialization of the temperature with sampling from the Maxwell Boltzmann distribution. I wrote it in the first input file. Yes, it was here, 600 Kelvin. But looks, the system choose a temperature that looks like whoa, the double of twice 600 Kelvin. Why? Because, as I said before, the initial state was guessed by randomly. So apparently there was it was a configuration where there was too much potential energy. So when I started the Verlet algorithm, the system took all this potential energy and this went into kinetic energy, so temperature. temperature. Then I switched on the thermostat at this point. You remember we did 100 steps of conjugate gradient. So this the very beginning. 100 is here. You see on the bottom left corner there is the x and y values for the plot. So here I switched on the Verlet or Carparinello. Then at 1100, that is here, I switched on the Nose-Hoover thermostat. You see the system goes down with the temperature very fast, and then it equilibrates around the value that I selected is 600 kelvins. Thanks God, it is the right value. Now I'm going to switch off the thermostat and let's see what happens. So, but this I can now see it. Why wasn't it also before? I don't know. So let's go ahead. So now our simulation is working very well, but now I'm going to explain you a little trick that can be useful if the simulation is more problematic. What do I mean with more problematic? I mean that maybe there is some energy exchange between the electronics degrees of freedom and the ionic degrees of freedom. So the kinetic energy of the electrons start to go up, and maybe, I don't know, maybe it is too high, or the forces are starting to become random numbers. So it may happen that you need to minimize again the ground state. So what we do? We do the same thing that we did at the beginning, but in this case we need only only one step, because one step is enough for minimizing. Note that we installed the one step in the input file, but in reality the code does 2 GG minimizations if the norm conserving pseudo potential is used. It does one minimization for t minus dt and one for t, then it computes the projector, and then it computes against the t minus dt wave functions. Okay, so it does, you select, you say one step, but inside the code does two steps of conjugate gradient to compute the projector over the occupied manifold. So this is easy to do and also very fast because we have only one step. So let's see the input file. Water 8.4 conjugate gradient protein. Okay, let's start model start. As always, I increase by one number directory read and number directory write. I do again conjugate gradient for the electrons, so no Verlet algorithm, no Carparinello. We are doing what I did. We are doing a Born-Oppenheimer for only one step, and ion temperature not controlled. So I switched off also the Nose-Hoover thermostat. Okay, so we do another minimization. Let's see if I forgot something. Okay, the time step I left the same as the Verlet algorithm with the Carparinello, so I don't have to use the ugly change time step input of the code. Everything is the same. Okay, the electronic mass, in fact, is ignored when you use conjugate gradient, but I left here, nothing happens. Okay, here everything is the same. I forgot to tell you, this part of the input file, the atomic position file, is the same that I used at the beginning. But if you use the restart feature of the code, this part will simply be ignored. So you have to put it. It is sufficient to copy and paste the atomic position that you have from the first input file, But the code will not use this position to do the computation. It is going to use the position read with from the folder number 52 with the start file. Okay, so this is a very fast calculation. Okay, there are some messages that the run are slow. Okay, I will go slower, but now it's almost finished the tutorial. So don't worry. What I was about to do? Okay, submit the minimization. This is a very fast step. For quantity.in. So now we are using, I'm doing this to use this trick. We compute a new ground state, and we compute a new ground state velocity, let's say. So we are happy. And why this is better than a velocity of 0? Because this is somewhat consistent with dynamics of the ions. It's like, suppose before the example with the water and the bowl. So you suppose that everything is moving. Or let's say accelerating. Is accelerating in this direction. Okay, the water is like this, and here I choose a velocity that is consistent with this acceleration. If I don't choose this, maybe it can go the other side like this, and then like this, and it's not okay. You will have at the end of the day more kinetic energy for the electrons. Also, if you start with 0, a velocity of 0, imagine that you are on a running car with a bowl of water on the top of the car. If the velocity of the water is consistent with the velocity of the car, okay, it's okay. If you put some water at rest on a car that is running, the water will start going out of the bowl, okay? It will gain kinetic energy. Okay, so I think that the optional step, I stress again, I repeat again, this is optional. In our case, it was not needed because our simulation was good. But if you have a problematic situation where the kinetic energy is increased, with this trick, you can cool down the electron near the ground state. Okay, for sure, this is finished. Okay, I get the new restart. As you see, the code did not copy new trajectories, new pieces of trajectory, because I did only one step. And since I asked the code to print the trajectory every time that the number of steps is a multiple of 10, in this case, did not print. The code did not print anything. So now we start the last step that is like the steps previous to the equilibration with the Nose-Hoover thermostat. And this is, we can see the input file. The CP water rate. We have number 5, the last step. Okay, you see always increase this number directory read and write to point to the right directory. Okay, then job, the long-running job seems finished. So now I want a lot more steps because now I want to calculate some thermodynamic quantities from the trajectories. We are going to compute the pair correlation function and the mean square displacement. So to compute these quantities, we need a lot more steps than 1,000. A lot more steps than 10,000 probably, but just to see something, now we put 10,000. We switch again on the CP, equation of motions. Okay. This is the input file. The time step is always the same. Pref is always the same. Everything is the same. The ion temperature not controlled. Ion velocity default. That means read them from the start file. Here nothing, and here I have always the same position that are not used by the code if you're using the restart feature. So let's submit it. Remote MPI run, quote rate 5. NVE, that means for constant number of atoms, constant volume, constant total energy. That is the microcanonical ensemble. As Professor Scandalo said before, if you want to compute dynamical properties like the diffusion coefficients, you have to use the microcanonical ensemble. That is the one with the right equation of motion for the ions. So if you use the thermostat adds some forces on the ions that are not physical. So you're not getting physical trajectories. You can get physical averages, but for dynamical quantities, no. Okay, this will take a little bit longer, like 10 minutes, or maybe. On SISSA it is about 5 minutes, but if somebody took 7 minutes, anyway, you can see what happens at the end. In the meantime, are there any questions? Let's see.
I think we took most of the question.
Okay.
Don't see any open.
Okay, maybe we can look at the trajectory that we have now.
Okay, so we leave space to the lab, no?
Leave space too?
No, I mean, is the explanation over?
I think so. We are waiting for the result of the last session,
sure, okay.
and then we are going to compute something interesting.
Okay, sure.
But we have to wait a little bit. There are some clusters where if you do rsync now, it crashes or something like that. I don't remember. So maybe it's not a good idea to do it now. By the way, you can run this script that will create again the trajectory that you can view with Ovito, for example. This you can do while you are waiting for the results. You see now it is longer, and atoms moves a little bit. By the way, this code is super slow in my virtual machine. I don't know how it runs in yours. By the way, you can see atom that moves. I can make some comments maybe on that. You see the coordinates are not wrapped inside the cell. The code always write unwrapped coordinates. This is because with those unwrapped coordinates, it is easier to compute the mean square displacement, for example. Okay, there is a question. Is there any tricks to restart the molecular dynamics simulation without the restart feature working, basically? Yes, exactly that. You can copy the last position from the input file, copy the last velocities from the output file to the input file. Be aware that the units of the velocities are somewhat tricky. What is the units? Atomic velocity you can hear. Okay, so the velocities has the units of okay, for the velocity you have position, let's say unit of length of a unit of time. This is the same as the atomic position input part, and this is always atomic units in the units of Carparinello. That means 2.4 times 10 to the minus 17 seconds. I've written this number on my desk because I always forgot it. And this is same as position. So those are the units of the velocities that you have to use if you use the input file. So basically you copy the position and velocities as is, because in the output it is Bohr over atomic units of time, so it is okay. You specify Bohr for the position, and that's it. Then you have to do the computation of the ground state with the conjugated gradient method. If you want, you can compute also the velocities of the wave function. That means if you use non-conserving pseudo-potential, and then you can start from this restart file. So you will produce a restart file with this conjugated gradient, and then you can run again the Verlet or whatever you want using this restart file as an input. And maybe I can mention in the meantime, maybe it's finished. Let's see. Remote skew. Oh, it's running. Okay. I can mention where you can find some documentation. Okay, you have this, and then you can have a look also to the repository. So if you Google Quantum Espresso GitLab, you end up with the repository. With this repository, Quantum Espresso is there, and you can find inside this folder CPV some documentation for the Carparinello method, and there is a user guide that is in the process of a lot of updates, where you can find some hints, some very useful information to use this code. There are a lot of stuff inside this file that I didn't say anything about, and there are also, yes, everything. There is the documentation for the autopilot module that is very useful when you want to do some experiment. Here there is a different file, and you see how can you change on the fly some parameters, like you can put a file in the folder of the simulation with this written inside, and the code will start when it reads the file, will change the parameter that you have written inside the file. This is a mailbox file. So there are these interesting features that you can use if you want. All this stuff is not necessary when you do a production run. So when you want to do your simulation for calculating your quantities of your system. Obviously, you are not going to change anything on the fly, but this is useful for experimenting at the beginning. It is faster. So if you want, for example, to see what happens if you use a larger time step, you can say, oh, let's try what happens. You put this file inside the folder, and the time step will instantly change, and you can see if the simulation explodes or not. The most common error that the codes outputs is ortho went bananas. That ortho is the part of the algorithm that it is an iterative algorithm that computes the orthonormatic constraints that are okay, that computes this, and it is iterative, and if something went wrong, usually the wave function become messed up, and this algorithm is not able anymore to orthonormalize the wave functions, and it prints out ortho went bananas. So if you see this message, it's very fun. Bananas. If you see this, usually you can try to lower the time step, or maybe you have lost. You had maybe you don't have a gap anymore, or maybe mu was too big. So it means that electrons are no more for sure in the ground state, and you have something very, very wrong. So you can you have to stop and look carefully at your simulation. Be careful that on some unstable systems, like for example, I had this issue on the old Marconi KNL cluster. Some probably hardware instabilities made the simulation unstable. So this error was appearing randomly during the simulation, but everything was okay. So it can be that due to hardware issue, you can get this error too. But usually, if you have this error and you look at the trajectory and you see that the electronic fictitious energy is going to the stars, you have to do something. Okay, let's see if it is finished. Connection. I lost the VPN, sorry. Okay. What happens to the VPN? My VPN stopped working. I'm not don't know why. It's always like that. So I stopped the share because I don't see the error message that my computer is giving to me. Activation failed. But sorry. Let's try to see if the other script works. No, it is in the post installed directory. Okay, now I don't know why in my host computer does not work. Okay. Okay, it works. Now we're seeing everything before the VPN stopped working again. Okay, now the trajectory should be a lot longer. So now I can run again this script that now computes also the pair correlation function and the mean square displacement. Okay, now we can look also at the thermodynamic quantities plot. Let's look at the temperature first. Okay, you see that okay, it looks okay. It equilibrated at the end of the day at something higher than 600 Kelvin. You see that the moment in which you switch off the thermostat is important. Here, the example, for example, I switched off the thermostat in a point when the temperature was slightly higher, and so I got a slightly higher temperature than 600 Kelvin. Let's see to all the other data. Okay, you see the system was oscillating around this total energy, but when I switched off the thermostat, the total energy was higher than the average, let's say, of the oscillations. So the temperature at the end is higher than 600. This is the potential energy. Okay, you see this on the high side of the oscillations. Then we can have a look at the constant of motion and everything. You see there is a jump. There is a jump because I switched off the thermostat, so there are no more the thermostat degrees of freedom, and the constant of motion of the Lagrangian changed because it's a different. The system is in a different state now, and it goes here. Let's see if it is constant enough. Okay, super constant. You see, it is really constant. So the constant of motion is okay. The electronic kinetic energy is okay. It is more or less a constant. And this is the physical constant, the physical total energy, kinetic energy of the ions plus potential energy that is calculated with the density functional theory. It's more or less a constant, so I think that simulation is okay. So we are happy. We are happy with it. If you want, you can have a look at the trajectory. Let's have a look at the trajectory. So after executing the analysis thing, you can have a bigger, longer trajectory. Okay, you see that some atoms went pretty far from their original positions, and they're going a lot away from the cell. So the system looks like a fluid or a gas, where we have really few particles, few water molecules. So it's hard to say what it is, this system. But anyway, we have it there. The analysis script, this is what is inside. You can have a look at it if you are interested, but it's not related to quantum espresso, so it's something more that I put here only to show you what it is possible to calculate with molecular dynamic trajectory. There are some commands that compute the mean square displacement and the pair correlation function. Now let's have a look at them. I prepared some scripts to show them. Plot, let's say let's start from the pair correlation function. Okay, this is the pair correlation function. On the x-axis, there is the radial distance in angstrom, and on the y-axis there are arbitrary units. These plots are not normalized. But let's look at the peak. You see there is a very big peak here. This is related to the oxygen-hydrogen bond, and you see it is right. It is about 1 angstrom. So we are happy because our water molecules looks like water molecules. So this is oxygen hydrogen pair correlation function. I remember you that is this is an histogram practically. So the code tries to calculate all the distance, in this case between hydrogens with a central atom that is oxygen. Maybe that is if I write somewhere. So suppose that here you have an oxygen, and then you have many hydrogens here, an oxygen here. And put random positions. So I look at all the distance between the central oxygen atoms and any other hydrogen atoms, and I put those distance, 1, 2, 3. I will have a list of them, and I did an histogram of this, and I have this blue plot. If I do the same, but I keep, for example, the central atom an hydrogen, then I compute hydrogen, the distance of other hydrogen atom with respect to these central hydrogen atoms, and I have I will have another distance, prime 1, prime 2, and a lot more, and I will have this plot here, the hydrogen-hydrogen pair correlation function. You see here you have a peak that is related to your oxygen, hydrogen. This is related to this distance, the first peak. You see it is around 1.5. It is true. This angle is almost 100 degrees, so it is okay. And then you have oxygen-oxygen correlation function, pair correlation function, and you see that two oxygens start to see each other at 2.5 something angstrom. So they are farther than the other molecules, the other atoms in the molecule. So this is it, and at the end, you see there is a lot of noise. The simulation is very small, and you cannot compute, you cannot have large statistics for these simulations. So this is noise. Then we can have a look at the mean square displacement. Then I will finish. It's almost the end. Okay, this is the script I prepared for you. It's nothing special. It's only some. Okay, this is a mean square displacement plot. You see, there is the oxygen and the hydrogen mean square displacement. What is mean square displacement? So, did I put a formula at the end? Okay, here it is. So you are computing an average. This is an average over the trajectory of, okay, here you have a sum over all the atoms, and you divide also by the number of the atoms of this type. So you pick, let's say, an oxygen atom or an hydrogen atom, let's say hydrogen. You have a starting position at t equals 0. Then this atom goes away during the trajectory. You have t equal 32, t equal 42, whatever, and you are here now. Whatever. And the mean square displacement is simply the difference between these positions, between the position at every given time and the initial position squared, and you get this plot here. So what can happen in this case? It can happen that if it is a solid, for example, the atom will always stay near its initial position, and so you expect that the mean square displacement here we have time does something like that. At the beginning, it will move a little bit, and it will stay still. But this is not what is happening here. So after an initial transition, let's say, initial transient moment, you can have some equilibrium behavior, let's say, that if the system is liquid or a gas, it is something like a line with a constant slope. So we have something here, then a line. And you can compute the diffusion coefficients by looking at the slope of the line. This is the diffusion coefficient, okay? So here it looks like we have a diffusing system. And another thing that you can notice from this plot is that the two lines here are more or less parallel. That is something that we are expecting since we have a molecular system. So the molecules are always bonded within themselves. So they are not dissociating. The hydrogens of the water molecules stay always near the oxygen of their water molecules. So they go together. Okay, so if we had a lot more time on the x-axis, we will see that the plots basically will go one on top of the other. Okay. Okay, so that's the end of the tutorial. And if there are any other question, I'm here. If not, we can meet later on the talk.
I would say we leave the Zoom open anyway, in
Okay.
case somebody, but we can stop the streaming, and we wish to see the participants tomorrow as well, and we thank you, Riccardo, very much for the lab. But definitely we leave the Zoom open in case sometimes needs help. We stay around and we can jump in if needed.
Okay, perfect.
Okay.
By the way, what was the time of the end of the?
I think 12:30.
Okay, so
yeah.
2 minutes. Perfect.
Yeah.
Okay.